This is lesson 9.5, Graham's and Dalton's gas laws. So Dalton's law of partial pressures states that at a constant temperature and volume, the total pressure of a mixture of gases is equal to the sum of the partial pressures of each individual gases. So the equation is the total pressure equals the pressure of the first partial pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas, and so on, depending on how many gases you have. You may only have 2, you may have 3, you may have 5. So it's just you're just going to keep adding on for how many other gases are a part of that mixture. So our first problem with Dalton's law says air contains oxygen, nitrogen, carbon dioxide, and other trace gases. We want to determine what the partial pressure of oxygen is. If the total pressure is 101.3 kilopascals and the partial pressures are nitrogen equals 79.10 kilopascals, carbon dioxide 0.040 kilopascals, and trace gases 0.94 kilopascals. So the equation is going to be P total equals the partial pressure of oxygen plus the partial pressure of nitrogen plus the partial pressure of carbon dioxide plus the partial pressure of the trace gases. So our total pressure is 101.3 kilopascals. So now I'm just plugging things into the equation. We're trying to find the partial pressure of oxygen. The partial pressure of nitrogen is 79.10 kilopascals. The partial pressure of carbon dioxide is 0.040 kilopascals. And those trace gases are 0.94 kilopascals. So we're going to solve for the partial pressure of oxygen. So we're going to add all the partial pressures that we know together, which is going to give us 80.08 kilopascals. And we're going to subtract that from both sides to get the partial pressure of oxygen by itself. So the partial pressure of oxygen is equal to 21.22 kilopascals. Okay. So the other gas law that we need to talk about is Graham's gas law. And Graham's gas law has to do with effusion. Effusion is the process where gas molecules pass through openings in a container and can be used to estimate the molar mass of a gas. So the rates of effusion of the gases at the same temperature and pressure are inversely proportional to the square root of their molar masses. So the equation and the rate of the first gas, A, divided by the rate of the second gas, B, equals, this is equal to the square root of the molar mass of B divided by the square root of the molar mass of A. And I represented molar mass with mm. So for Graham's gas law, it says compare the effusion rates of hydrogen and oxygen at the same temperature and pressure. So our equation, in order to compare the rates, we are going to do the square root of the molar masses of these gases. So because we know what these gases are, we can just go straight to the square root of the molar masses. So oxygen, average atomic mass is 16. Oxygen is diatomic, so that's going to make the molar mass be 32 grams per mole. And then hydrogen is also diatomic. The average atomic mass is 1.01, so that's going to make the molar mass 2.02 grams per mole. And this is going to be equal to 3.98. What this is saying is that hydrogen effuses 3.98 times faster than oxygen. Okay. So that's it for the two gas laws for today. You have practice on page 13 in your packet. Go ahead and take a look at that. Stop by and ask me if you have any questions. Thanks for stopping by. Have a great day.